Okay, here we're looking at practice test 4 and we're looking at the first question, part A. And I've drawn it out here. We have a ball attached to a string. The string is 8.34 meters and the ball is 0.38 kilograms. What is basically happening in this question is the ball starts at this position, it swings towards the spring, it makes contact with the spring and the ball move to the right in this direction. The spring is compressed. Once the spring is compressed, it releases back out the other way and it comes back away from the wall and it launches the ball back away from the wall. What we have been asked in the question is to find the time for one complete cycle of this motion. So I guess the hardest bit about this question is working out what's happening. We have the ball starting here, going towards the spring, then it moves a little bit further with the spring, it comes back out, and then without the spring, it moves back out to its original position. We have equations that allow us to calculate what this period of the motion is. So firstly, what is the period of motion for the pendulum part? Ignoring the spring part for the moment, what is the period of the pendulum component? The equation for this part of the motion is 2 pi L divided by G, where L is the length of the string and G is gravity. Recall that the period of the pendulum swing is not related or dependent upon the mass that is hanging on the end. So this describes the period of the pendulum. Now we also need to know what describes the period of the spring. We have an equation for this. It's 2 pi square root of m divided by k, where k is the spring constant, which we've been given, 26 newtons per meter, and m is the mass on the end of the spring. Now in this question, we're assuming that the 0.38 kilogram mass is actually attached to the end of the spring as the spring compresses and stretches back out again. Now in this motion, we can see that when the ball and the pendulum string get to this part, which would be considered equilibrium, that would be 1/4 of the motion. It doesn't go through the other half of the motion. It completes this first quarter, then it does its spring motion, and then it completes the second quarter. So the whole pendulum motion is actually half of the total period for the pendulum swing. And it's the same thing over here with the spring. It goes 1/4 of the way in and then 1/4 of the way out. So it doesn't, if this is our equilibrium position, which we know it is, it doesn't expand out the other way. So this is only half of the spring period. So now what we can do is let's work out what each of these periods are to begin with. Now, these two here combined will give us the total period of the cycle. So therefore, the total period of the cycle is half of the period of the pendulum plus half of the period of the spring. And then when you do that, you get 3.3 seconds. This question's pretty tough. So if you were to, for example, draw this diagram and recognize that you're covering half of the period of the pendulum and half of the period of the spring, you get a mark for that. If you were to actually identify these equations, you get a mark for each one. If you were to actually work out what each of the periods are, you get 2 marks for each of those. If you were to work out this equation, that the total period of the cycle is half of the period of the pendulum plus half of the period of the spring, you get a mark for that. and then you get another 2 marks if you actually got out the correct answer. So for this question, you get 10 marks. Okay, so let's move on to part B, where we have a sound source that emits waves uniformly in all directions, which I have drawn here. Point B is twice as far away from the source as point A. So in part I, we need to calculate the relationship between the intensities at point A and point B. Now from our formula sheet, we can see that we have a formula for intensity. It's power divided by area. Because this is uniform in all directions, the area is just the surface area of a sphere. So we can say that the intensity is power divided by 4 pi r squared. Now here we can say that the distance from the source to point A is RA, and the distance from the source to point B is RB, which is twice the distance of RA. Therefore, we can say that the intensity at A is power divided by 4 pi RA squared. The intensity at B is power divided by 4 pi RB squared, which is equal to 4 pi R 2RA squared, because remember RB is twice as far as RA, which means we have power, if this becomes a 4 and then it's RA squared, so it's going to be a quarter power over 4 pi RA squared, which equals a quarter of the intensity at A. Therefore, the intensity B is a quarter of the intensity at A. For this part, if you correctly identified these equations, you got a mark for that, and if you got the right answer, you got another mark for that. Part 2I is asking us about the displacement amplitudes, S max, at points A and B. So now we need an equation for S max. We have our intensities, we've just calculated them, so let's try and find a formula that has both intensity and S max in it. And from our formula sheet, so what we can do with this equation is actually rearrange it to get at S max on its own. Okay, so we have our formula here for the displacement amplitude, where we have omega, which is the angular frequency, we have the wave speed, which is v, the density of the medium is rho, and we obviously have our intensity here. So now we can just simply sub in everything that we know and compare the two displacement amplitudes. So let's do it first for A, because that's easy. And now let's do it for B, but we'll do it for B in terms of the intensity at A. Cool. So for this question, if you worked out what this formula was here, for the displacement amplitude, you got a mark. And then if you got out the correct answer, in which the displacement amplitude at B is half of that at A, you got another mark. For 3i, it wants us to calculate what the relationship between the decibel levels at points A and B are. So again, let's look towards our formula sheet to work out what formulas we have for decibel levels. Decibel is the symbol beta, and it's given by 10 log base 10 intensity divided by our reference intensity, which is 1 times 10 to the minus 12 watts per square meter. So now all we have to do is calculate this for A and B. So let's do A first, because that's the easier one. And now let's write the same thing down for B. Okay, so the easiest way to compare these is by remembering our logarithmic laws. So the way that we're going to do this is by doing the decibels at A minus the decibel level at B. And the reason we do this will become evident really shortly. And it's purely because of the way that we can treat the logs. Now, log laws are really great things because when you're subtracting two logarithms with the same base, you can just divide what's actually in those logs. So for this, we would say 10 log base 10, and we're going to divide one by the other. So it's going to be A, the first one, divided by B, the second one. So here we can see our reference intensities cancel. Same thing with our intensities at A. We're now dividing by a quarter, therefore it's going to be 10 log base 10 of 4, because when you divide by a quarter, it's the same as multiplying by 4, and you end up with 6. Therefore, the decibels at A minus B is going to equal 6. For this question, if you got out these equations for A and B, you got a mark. If you got down to this point where you were comparing the two by subtracting them, you got another mark, and then if you got the correct answer, you got a third mark. And for part 4, we're now looking for the pressure amplitude, delta P max, and the displacement amplitude, S max. We've been told a few different things like the amplitude at A, which I've written down, the frequency, the velocity of sound, and the density of the medium. So let's actually go back to our formula sheet and work out what our equations are. So we have an equation for delta P max. Now you'll recall that in the previous part we actually got an equation out for S max. I'll just write it again over here. Okay, so now we can just sub in S max over here. Let's do the appropriate cancellations, and we'll actually take v and rho into this square root here. Cool. So we have a pretty simple equation here. Now we can just sub in what we know to actually work out what the pressure amplitude is. Then when we do that, we get 12.8 times 10 to the minus 3 newtons per square meter. And then for S max, we actually don't know what our omega is. We have to get omega in terms of frequency. Omega is 2 pi f, and we have our frequency. There's a couple of ways we can do it. We can either use this equation here, which is slightly longer, or we can actually rearrange this equation here and get S max equals delta P max, which we've already worked out, divided by V times rho times omega, which is actually going to be delta P max divided by V times rho times 2 pi f. So let's sub in everything we know. Then when you do that, you get 4.95 times 10 to the minus 9 meters, or that's actually 4.95 nanometers. And finally, we have to comment on our results with respect to the efficiency of the human ear. So for example, this is the pressure amplitude that we got, 12.8 times 10 to the minus 3. So we can say that the pressure amplitude is very small, and we can even say that it's much smaller than atmospheric pressure. Therefore, human ears are very sensitive. For this question, if you got both of these equations out for P max and S max, you got a mark each for those. If you got the correct answers out, you got a mark each for those. And then if you had something sensible written about the human ear, you would get 2 marks for that. Okay, so for part C, we're looking at 2 trucks. I've drawn them here that are travelling towards each other at the same speed. And they're far apart enough, they're in different lanes, but they're far apart enough that they're essentially head on. And one driver, our observer here, is hearing the horn of the other one. So we can call the one who's hearing the noise or the horn the observer, and the one who's making the noise the source. So we know that one driver hears the horn of the other truck at a frequency that is 1.14 times the frequency that he would hear if both trucks were stationary. I've written that here as f prime equals 1.14 f, where this f here is the frequency of what the horn is. And we can take the speed of sound to be 343 meters as told in the question. I've written that down here too. So for part I, it's asking us at what speed is each truck moving. Now we know that this is a Doppler shift equation. So let's write down our equation for Doppler shift. Okay, we've got the equation here where V I have put down as the speed of sound, Vs is the speed of our source, and VO is the speed of our observer. F is the frequency if they weren't moving, and F prime is the frequency that the observer detects when they are moving. So the first question that we need to ask ourselves is, do we use plus or minus for the numerator and the denominator? Well, the thing with that is we need to look at in which direction are the trucks moving. They're moving towards each other, which means that their movement is actually going to cause the frequency that is observed, the frequency that is detected, to be higher than what it would be if they were stationary. So we need to set both of these plus or minuses such that they would actually increase f prime. So if we think about the numerator, how do we set plus or minus to make f prime larger than f? Well, we would set it as plus. So that would be plus v naught. And then what do we do for the denominator? Well, since it's the denominator, that means we have to do the opposite. So that would be minus vs. We were also told that the trucks are moving at the same speed, therefore we can simplify this even further by saying v plus vt divided by v minus vt. We were also told that the frequency detected is 1.14 times what it would be detected if they weren't moving, so we can sub that straight in. And now what we have to do is solve this for vt. Cool. So for this part, we get 22.4 meters per second is the speed that the trucks are traveling. For this question, if you got to this part here, where you assigned pluses and minuses to the equation for the Doppler shift, you got 2 marks. And then if you got the correct answer out and subbed everything in, you also got 2 marks. For part 2i, I'll just do it up here. We've been told that the driver that is hearing the horn stops. So now this truck is no longer moving, and we want to know what frequency does he hear now and what is the wavelength of the sound observed by the stationary driver. So first things first, what have we been told? While he was moving, the frequency was 800 hertz. That would indicate that f prime is 800 hertz. Now, for our new equation, it's exactly the same as what it was before, except it's slightly more simple. So let's write this down. So we know what VT is. It's at 22.4 meters per second. Now we have F prime, but that was when they were both moving. So what we can do actually is use this to calculate what F actually is, and then we need to calculate what our new F prime is. So therefore, to calculate F, remember that F prime before was 1.14 times F. We were told that originally. Therefore, 800 equals 1.14 F. Therefore, F equals 800 divided by 1.14, which is roughly 702 hertz. So then we can put that straight into this equation, along with everything else. And then when we do that, we get 751 hertz. So that's answering the first part. What frequency does he hear now? The next part is, what is the wavelength of the sound observed by the stationary driver? Let me just get rid of some of this. So now we want to know what the wavelength is. And we know what our formula for wavelength is. It's just velocity divided by frequency. And we know what the speed of sound is, 343 divided by our 751 hertz, and we get 0.457 meters, 45.7 centimeters. So for this question, if you correctly worked out that the frequency of the horn is 702 hertz, you got a mark for that. If you got this formula here, with the subbed in values correct, you got a mark for that. If you got the correct answer out, you got another mark. And then finally, if you worked out what the wavelength is, you got another mark.